Hey Math Learners, and welcome to Module 6, which is all about parametric and polar curves. I wanted to walk through just this first example, get you started on it. So pause this video, rewind it, fast forward it, do what you need to make it useful, and of course, join me in office hours. So this first example right here is a parametric curve, and what that means is that we have an equation that defines x and a separate equation that defines y. So let's go ahead and let's graph this curve. So our equation that defines x is 2 times t. So this would be negative 3 times 2, or negative 6. Negative 2 times 2, or negative 4. Negative 2, 0, 2, 4, 6. And then we have a separate equation that defines y. Y is going to be t squared. So here we have 9, 4, 1, 0, 1, 4, 9. And now together we can graph a new output. Our new output is going to be x, comma, y. So that first point we're going to graph right here, we can kind of skip t and just graph negative 6 up 9. And that next point we're going to graph is negative 4, 4. And then we'll go ahead and graph negative 2, 1, 0, 0, 2, positive 1, 4, 4, and 6, 9. Positive 6, positive 9. If this curve is looking familiar, that's a good thing. Let's connect the dots to see what we've got going on here. So there's our first graph. That is how you would graph a parametric curve. You define your x's, you define your y's based on t, and then you graph it without t. If I wanted to, I could put some direction in this, showing that this actually connects to this point, because that was t equals negative 3, t equals negative 2, t equals negative 1, t equals 0, t equals positive 1, t equals positive 2, t equals positive 3. That now actually shows that direction or time element of the parametric curve. So hopefully that helps you get started graphing parametric curves. The next question asks to write the equation of that function in just regular old Cartesian or rectangular coordinates, as it's one recognizable function. Hopefully you do recognize this is a parabola starting at y equals x squared, but it's been transformed a little bit. You decide whether it's been shifted up, down, right, left, whether the rate of change has increased or decreased, and where that is actually going to be represented in this equation. Again, I just wanted to kind of kick off how you're supposed to do these. Follow that same process when you get to this set of equations right here. Again, plug in your t values to determine your x values, plug in the t values again to determine the y values, but then we just graph x, comma, y. And then the last one you'll be looking at right here, same idea, only now we've been given theta. So theta is our new t, which means that if we plug in angles, don't plug in 0, 1, 2, 3, 4, 5, plug in some angles. And if you think about sine and cosine, think about angles that would make sense on your unit circle, not just numbers 1, 2, 3, 4, 5, but maybe thinking of using negative pi. You could even be as detailed as negative 3 pi over 4, negative pi over 2, negative pi over 4, 0, pi over 4, pi over 2, 3 pi over 4, and pi. Those are the values I might choose. Or if you wanted to just go with the quadrants that you know, skip those pi over 4 angles and just do that. Negative pi, you could then incorporate negative 3 pi over 2, and even negative 2 pi, which would make this guy be 3 pi over 2 and 2 pi. Then you would get 2 full periods in there. So that might be another way to choose some angles on number 3. But it's going to look the same, where we have to plug our theta values in to get our x's and our theta values in to get our y's. But then when we graph it, we are just graphing x, comma, y. So this column, comma, this column will be our ordered pair. Okay, have some fun on these. This is one of my favorite topics in math, one of my favorite things to do, my favorite things to teach, just because it feels like a puzzle. Come join me in office hours if you want to check your work.